Okay. Hello class. Today we are going to discuss system representation in the Z domain. How to represent, how to analyze discrete time systems using Z domain. So in this discrete time system analysis in DSP, there are mainly two ways to represent discrete time systems. First one, as you can see, is the time domain representation. It's called time domain representation of discrete time systems. So input signal x of n and output signal y of n represented as a function of time. Our independent variable is n here. So we call it a waveform. Amplitude versus time representation of input output signals, we call it a waveform. Here, this in time domain representation of discrete time signals, the equation, mathematical modeling of these systems, equation which relates input and output, we call it difference equation. It's called difference equation, mathematical modeling of discrete time systems in time domain representation. The system here, the discrete time system, represented by a sequence called impulse response. We are discussing time domain view of a system, discrete time system. So h of n is a sequence which represents the discrete time system in time domain. And we have discussed also what we call it convolution sum. It is a mathematical method formula to determine a response of a discrete time system, y of n, given the input and impulse response. If input, for any arbitrary input, by convolution sum of x of n and h of n, we can determine the response y of n. That's what generally time domain representation of a discrete time system. When you come to the frequency domain here, the input and output signals, now they are function of independent variable. In this case, it is the frequency. So amplitude versus frequency. This case, we call it what? We call it a spectrum. If you plot the amplitude of your signal as a function of frequency, it's called the spectrum. The time domain, as we have seen, it signals amplitude as a function of n time. That's a waveform. Now, second way of representation, second way of analyzing discrete time signals as a function of frequency. As you can see here, x is a function of angular frequency, output also a function of angular frequency. In this case, we use equation or function to represent the system is represented by a function called transfer function or system equation. The time domain, we use what? We use what we call it impulse response, h of n. When you come to frequency domain, it is h of omega, what we call it transfer function or system equation. This equation represents the system. So you can plot determine magnitude and phase response of the system. We call it in general the frequency response of the system. This is second approach, second view, what we call it frequency domain view. So the first one we have discussed is time domain view. Second one is the frequency domain view. But there is another representation view to analyze, to represent discrete time systems, what we call it Z domain approach. Z domain representation, as you can see here in the middle. So you can say Z domain is general form of the frequency domain. But it's very important to understand Z domain as a link between the two approaches. What's the first approach? Time domain approach. Second one, frequency domain approach. In many books, in many cases, they consider Z domain as part of frequency domain. But it's very important to understand Z domain as a link between the two type of approaches, time domain and frequency domain. In between, we have Z domain approach. It's very simple for analysis, for design, for presentation of discrete time systems. The Z domain approach is very simple and important. So here, the input signal X of Z and H of Z represented as a function of a variable called Z. Z is a complex frequency variable which contains R, magnitude, and e raised to j omega, where it is a phase. That variable, we call it Z, a complex frequency variable Z. So signals here, input signal X of Z and output signal Y of Z, they are as a function of a variable called Z. Now, just like impulse response in time domain, H of omega transfer function in frequency domain, when you come to Z domain, the system is represented by a transfer function H of Z. We'll see that using examples. Another very important thing we are going to discuss in the Z domain view of a discrete time system is Z plane. Z plane, because Z is a complex frequency variable, we have the real part, real axis, and we have the imaginary axis here. Because Z is complex frequency variable, this plane, we call it Z plane. If you take, as we have discussed, Z is equal to complex frequency variable magnitude R e raised to j omega, right? So when R is equal to 1 for magnitude 1, our circle will be a unit circle. So you can increase frequencies. This is positive frequency on this side and negative frequency this side. This circle is a unit circle where magnitude R is equal to 1, right? So when you increase the frequency, it will go like this, it's circular. So this is Z plane. We'll discuss this using examples. Z plane. And another important point we are going to discuss here will be poles and zeros of a system. All originated from what? All originated from the h of z. From h of z, you can determine poles and zeros. If you plot it on z plane, you can determine the characteristics of this discrete time system. We'll discuss that using examples. Okay, before we come to the z domain, let's see some example on time domain as a revision. Time domain view of discrete time system. So let's see this system, very simple discrete time system, where x of n as a function of time n, and output also as a function of time n. If input output signals represented as a function of time, we call it what? Here you see our independent variable is n. Signals, input output signals as a function of time. Because we are discussing what? We are discussing the time domain approach. What is next? The difference equation for this system. Equation which relates input and output in this case. So let's write the difference equation here. Okay, here is the delay element. As you know, three basic elements when you draw this signal flow diagram of a discrete time system. You need delay element. Delay the signal by single unit. Here is the multiplier. Here is the adder. These are three basic components, elements of a discrete time system. Okay, so the output here applied to the delay element. So here we'll have y of n, delay means n minus 1, delayed by 1 unit. So this delayed output, here is a multiplier, multiplied by how much? By 1.3. So at this point, we'll have 1.3, the multiplier constant, times y n minus 1. Right? So it's delayed by 1 first, then it's multiplied by 1.3. This is a 1.3 multiplier. It comes here. This yn minus 1, again delayed by 1, it will be yn minus n minus 2. So the yn minus 1 again delayed by 1 unit, because this is another delay element. So it will be yn minus 2. So this yn minus 2 multiplied by another constant, negative 0.7. So at this point, what do we have? Minus 0.7 times yn minus 2. That's our signal here, n minus 2. Okay. Then this signal comes here, added together with 1.3 yn minus 1. Again, here the input is added. These are adder circuits. Will give us what? It will give us the output. So y is what? Y is equal to, as you can see here, the difference equation. Output, this output is equal to input, which comes from the here, x of n, plus, this is adder circuit here, 1.3 n minus 1. This signal also comes as a feedback. You see here, output is first delayed by 1 and multiplied by 1.3, added together to the input side, this one. Another signal, this part, yn minus 2, the output delayed by 2 times, because we have here 2 delay elements, is series, multiplied by a constant 0.7 and added together to the input side. So this equation is our difference equation. Okay, so when you write equation which relates input and output for time domain, we call it a difference equation. Okay, now we have the difference equation. Okay, we have the difference equation here. Why the difference equation for our system? Now let's see the impulse response of a system. Okay, so you can collect output on one side, input one side. So y of n, take this one on the other side, this also on the other side, to collect all output on one side. So when you take this on the other side, it will be negative. This negative will be positive. So input on one side, output on the other side. Okay. Now this system, the system you see here in time domain, you can write difference equation which relates y and x, right? Input, output. Now let's see how to write MATLAB program to determine the impulse response of this system. What is h of n? Very important function about the system in time domain is what? Is the impulse response h of n. Now, so this is our MATLAB program. Here you see b, variable b is the coefficient of input in our difference equation. So what is the coefficient of the input side, x of n? Only 1, right? A is the coefficient of output side in your difference equation. So what is the coefficient of y of n? It is 1. So we put it here. What's the coefficient of yn minus 1? Minus 1.3. We put it here. And the coefficient of yn minus 2 is 0.7. We put it here. Okay. So B and A represents what? The coefficients of the difference equation. If, as we have discussed, here our system is linear time invariant system because the coefficients are constants. If the coefficients in your difference equation are constants, your system is linear time invariant system. So B and A, we take only coefficients from the difference equation. So this is our system. System represented by what? In your program. In this program, our system represented by the difference from the difference equation. First, we write the difference equation of your system, which is called mathematical modeling. Then, in your program, take the coefficients from this difference equation, that is B and A. Next, as you can see here, from this part up to this part, up to x, we generate a sequence called unit impulse sequence, delta n. B and A represents what? B and A represents our system. Right? From the difference equation, we get the difference equation from the signal flow diagram. From the difference equation, we take the coefficients, and here we generate impulse unit impulse sequence. So as you can see here, n, we represent n, the time range from -10, from -10, you can take any time range, it doesn't matter, up to what? Up to 40, positive 40. We specify n time from, as you can see here, we specify the time from -40, -10 up to 40. Next, we divide this time range into 3. So n1 here, n1 from -10 up to -1. Okay, this range we call it, we denote it as n1. n2 contains only one sample, which is time 0. Time 0, this we call it n2. Okay, I'm dividing n into 3 time ranges, n2. Next, n3 from 1 up to, from +1 up to 40, this time range, we call it n3. Okay, so that's the specified time from -10 up to 40, divide into 3 time ranges. Next, x1, here you see x1, in the time range of n1, our impulse, unit impulse, all samples are 0. As you know, impulse only amplitude 1 at n is equal to 0, right? So impulse response from the definition, it is 1 at n is equal to 0. 0 for n different from 0. Okay, so it's only 1 at n is equal to 0. So as you can see here in the n1 range, in our program you see here lengths of n1. In the lengths of n1, all samples are zeros. Okay, because the definition of the impulse response, sorry, the definition of the unit sample sequence. How about in the lengths of n2? So we call this from -10 up to -1. The length of n1, we call it x1, our signal x1, all samples zeros. Second signal x2, only the length of n2. What is n2? n2 contains only 0. At 0, what is the impulse response? It is 1. So as you can see here, x2 is 1s in MATLAB, which applies a magnitude 1. Next, x3. So we call this x2 only at n is equal to 0. Start from 1 up to 40, we call it x3. Again, from 1 to 40, all sample values are 0 because it is unit impulse. So x3 also 0, where the range of n3. Okay. Now combine this x1, x2, x3 into one x here. We call this process concatenation. X is x1, x2, x3. So x is what? X is our impulse response. We generate impulse response. Right? Now, if you have a system like this, if you apply input, the impulse response, what will be the output? Sorry, the input is the unit sample, unit impulse sequence. So unit impulse sequence delta n as input. What will be the output? The output is called impulse response h of n. That's why it's called impulse response. So how to find h of n? How to find h of n? What you have to do is apply delta n into your input, find the output. If you apply delta n for your any system, if you apply delta n as input, the output is called impulse response. So here, as you can see here, h impulse response, because I need to find h of n for my system here. So using a MATLAB function called filter, you can determine the output of this system. Why we call it h? In this case, y is equal to h. Why? Because x is equal to impulse. If x is impulse, unit impulse, the output becomes h. Right? So filter is a function which determines the output of a discrete time system. What's B and A? They are the system. B and A is, look here, for any discrete time system, you write difference equation, right? Like this. So from the difference equation, you get B and A. Okay, coefficients. So this is input. This will be the output for that discrete time system. So you can determine output by in MATLAB by using a function filter. Okay, so we write filter B comma A. B comma A are the systems. What is the input? X. So same thing I have done here. I generate input. Here is B and A, which represents what? The system itself. The next I generate, this step I generate impulse. We call this X and apply it to the filter function. BA is the system. You will get what? Impulse response, H. Why? Because the input is impulse. You can apply any input, no problem. But in this particular case, what I need is the impulse response of the system. So that's why we apply the unit sample, unit impulse sequence. So let's see. Let's run this program in our MATLAB. Okay. So as you can see here in our difference equation, B is 1, the input side. A is a coefficient on output side, 1 minus 1.30.7. All these are to generate the impulse signal, unit impulse. Then impulse response is equal to filter B and A coefficients, our system. What is X? X is here, the input. In this particular example, we apply impulse. When you apply unit impulse, the output will be H. Right? Then stem, which is used to plot this discrete time impulse. Then our title, impulse response, x-axis n and y-axis h of n. So let's run this program. So this is editor window. As you can see here, in order to run, I have to copy it and take it to command window and paste it here, then enter. So we'll see the response here. So this is the impulse response. As you can see here, the title, impulse response. time n, y-axis is h of n. Okay, this is h of n, impulse response. Okay, so as you can see here, the impulse response from the MATLAB. This is impulse response of this system. Okay. Now, if you get the impulse response h of n, you can determine. Before that, let's see one more example. So this system, this is finite impulse response discrete time system example. Here you see the difference equation. Y of n is equal to 0.5 x of n. Look here, x of n comes here multiplied by 0.5 plus, this is another signal comes from this side also, right? So x is delayed by 1, so it becomes xn minus 1 multiplied by again 0.5 and added together, it will give us the output. So output will be 0.5 x of n, this signal, and 0.5 delayed input. This case, signal input signal directly, but in this case, first delayed by 1 multiplied by 0.5, it will come to the output y. So here we have the difference equation, right? The difference equation. So what are the coefficients here? Output side coefficient 1, input side 0.5 and 0.5. So let's go to our program, MATLAB program. Okay, so B is input side, so input side 0.5, 0.5. Output side only y of n, so the coefficient will be 1. A is the coefficient of the output. Now, let me arrange the time range. Now let's see from -3 up to 10 only. Let's see. So this will be minus from -3 up to -1. N2 is 0. Here from 1 up to 10. Okay. Now now you see the system is another system. If you change A and B, the system will be different. This represents your system from the difference equation. What are these? This is your input. In this case, part impulse. If you apply input impulse, this is your system. The filter function calculates the output. If your input is impulse, the output is impulse response. Then you plot it. So let's run this program. Now you see the impulse response of the system. You see the previous system, the impulse response is different. So we have seen this is the impulse, the first system we have discussed. This system, the impulse response looks like this. It is decreasing oscillation, right? You see it's discrete time, but it's decreasing oscillation type impulse response. Second system, this one, the impulse response looks like this. We have done it in MATLAB. Okay, so we have seen difference equation, we have seen impulse response. Next is what? Convolution sum. What's convolution sum means? If you know h of n, if you know for any input, you can calculate the output, right? By using convolution sum formula, what you can see here. Okay, convolution sum formula is the formula which input is given, h of n is given for any arbitrary input. You can determine the response of a system. Let's see this on MATLAB. Okay, so look here. Now we know h of, right? H, the impulse response. So let's calculate the, let's take input. Input, let's say our input R, any variable. Let's apply sinusoidal, discrete time sinusoidal as input to the system. Sine 2 times I times N. This is our input, right? For the system, for our system, from here, this is our system. This is impulse, unit impulse, and we calculate H using filter. Now we know H, the impulse response. Now what will be the output? What will be the output? Y. Y is equal to convolution. By using convolution, conv in MATLAB, convolution, what is the, we are convolving input, in our case is X. What is X? This sinusoidal, right? Sorry, R. R, here I generate input sinusoidal with amplitude 2, comma, convolution of input and H, right? Impulse response. If you convolve this, you will get, as you can see here, it gives us what? The output. Y. Convolution. All output samples here you can see from this output. Y. By convolution of what? The any arbitrary input you can apply. If you have H, for any input you can calculate output by using convolution sum formula. This is what we have discussed. In chapter 2, if you remember. Okay, now second approach, our topic will be the Z domain view. As we have discussed, you can analyze, represent, or design discrete time systems in three different, basically two different approaches, frequency domain and time domain, but more general, frequency domain approach called Z domain, which is relatively easiest way for analysis design, what you call it Z approach, Z domain analysis. So in this case, let's take this system. So X and Y represents by what? In this case as a function of time, but in Z domain they will be as a function of Z. X of n will be transformed to X of Z, output also transformed. How we are going to transform? Summation Y of n z the power of minus n from minus infinity up to infinity. This is z transform we have discussed previously, right? So in this manner, y of n transformed to y of z. Similarly, x of n transformed to x of z. We are transforming our signals in z domain form. So x of n becomes x of z now. Okay, everything as a function of z. Y of n becomes y of z. Okay. So summation and multiplication here we have other circuit, right? To y of z, okay, from input side. Then the output delayed by 1 in time domain. Look here, the second property of Z transform. We call it time shifting property. So if the Z transform of x of n is x of z, now in time domain, if you shift your signal by some constant n naught, what will be the effect on Z transform? X of z will be simply multiplied by z the power of minus n naught. For example, if x of n, you have discussed this property also for Laplace transform. If the transform of x of n is x of z, if you shift your signal in time domain by, let's say, 1, what will be the z transform from the time shifting property of Z transform? Here we'll discuss two properties, linearity and time shifting. So if you shift your signal in time domain by 1, what will happen on Z domain? Z the power of minus 1, because this is 1, shift is 1. Simply x of z multiplied by z the power of the shifting constant. If you shift your signal by 2 in time domain, what will be the transform? Simply x of z multiplied by z the power of minus 2. If you shift it by 3, multiply x of z by z the power of minus 3. Now if you shift it, if it is n plus 3, what will happen to the z transform? X of z multiplied by z the power of, now it will be positive 3. Okay, this case minus 1, here is minus 1. Minus 2 here, multiplied by minus 2. Plus 3 here, z the power of 3. Okay, so shifting in time domain is multiplication in z domain. So here, in time domain, we represented by this delay. So if you apply y of n as input, the output will be y of n minus 1. Okay, but in that domain, it is different. Now I'm giving you another view of a system, discrete time system, Z domain view. Okay, so shift in time domain, but when you are working in Z domain, what you have to do? Multiply it by Z the power of minus 1. Because look here, x n minus 1 will be x of z multiplied by what? Z the power of minus 1. So what will be the output? It's multiplication now. Z the power of minus 1 times y of z. Okay. Then this signal comes here multiplied by a constant. This is a multiplier, right? You see here in the time domain representation, multiplier. In Z domain also, multiplier. If you multiply in time domain, you multiply in Z domain. Multiplication, no change. This property is called what? Linearity. Look here. X of 1 is x1z. Okay? When you multiply x of 1 by some constant a, same x1z multiplied by a. So multiplication does not affect Z domain. Okay, so same multiplication in time domain here. It's 1.3. We multiply in Z domain. By how much? 1.3. It comes here. There is what? Other. Same thing for addition. In time domain, when you took addition, in Z domain also, same addition. Why? Again, because of what? Linearity property. Look here. When you x1, x1z, x2, x2z, when you add these two signals together, here you see the addition, Z transform also addition. Okay. So this is linearity property of Z transform. Okay. So it comes here added together. Another delay element represented in Z domain by what? Z minus. Why we write minus 1 only? Because if you delay by 1, x of z multiplied by z minus 1. That's why we write z minus. Z minus 1 means unit delay. Okay. So what will be the output? This one delayed by 1 again, z the power of minus 1, z the power of minus 2, y of z. Another multiplier, same multiplier in z domain, right? As you can see here, another multiplier by 0.7. So minus 0.7 is here. This signal go and add it together with input. Now everything, look here. In this case is time domain view. Signals as a function of time, input output signals. Okay. Now we transform this system, discrete time system, from this time domain to Z domain. X of n becomes x of z, y of n becomes y of z. These delay elements, okay, in this case it is delay yn minus 1 in time domain, right? What will happen in frequency domain? Multiplication by z the power of minus 1. That's only difference here from the shifting property of z domain. Now we see here, same system, but represented in different domain. We call it Z domain. Why we need to transform system from time domain to Z domain? Because for mathematical analysis, for design, Z domain is much easier relatively. So the difference equation in time domain, system represented by what? System represented by difference equation. Now, system transformed. Y of n becomes what? Y of z. Multiplication by a constant is the same. Why? Because of which property? The linearity property. Yn minus 1 means shifting in time domain is multiplied by z minus 1, y of z. I'm transforming this discrete time difference equation into Z domain. How we are going to transform this? 0.7 as it is because of linearity property. Summation as it is because of linearity property again. Because of shift property, what is Z transform of Yn minus 2? Shift by how much? By 2. Then Y of Z multiplied by Z the power of minus 2 is equal to X of N transformed to X of Z. Okay, this is how we are going to transform difference equation into Z domain. So this difference equation Y of N in time domain, same system represented in Z domain. Sorry, let me draw it here once more. Z domain representation. Here. Here. So output in function of Z, input a function of Z. Now this is a domain representation. So this is time domain difference equation. Everything is transformed into Z domain. Let's see another example here. Let's say our difference equation n y of n plus 3 y n minus 1 plus 5 y n minus 3 is equal to x of n minus x of n minus 1. Let's say this is the difference equation. Now, how we are going to transform it into Z domain? So y of n becomes y of z, right? Plus linearity. So plus, you see here, multiplied by constant. Z is also multiplied by constant. If you are two signals together and if you transform it into Z domain, it will be summation also. So 3 will come here. What is the Z transform of Yn minus 1? Z the power of minus 1 y of Z. What's the transform of this? Plus 5 Yn minus 3 means in Z domain, Z the power of minus 3 times y of Z. Okay, is equal to what's transform of x of n? There is no shift, so x of Z. But in this case, there is shift by 1, so it will be Z the power of minus 1 x of Z. If signal is shifted in time domain, you have to multiply it by Z the power of the shifting constant. Look here. Now this difference equation transformed into Z domain. Okay, using which properties? In this case, we use linearity property and time shifting property of Z transform. Okay. Now, once you transform it into Z domain, take y of z common in this example. If you take y of z common, what do you get here? Coefficient of y of z is 1 plus, if you take y of z common, it will be 3 the power of, so 3 times z the power of minus 1 plus, here it is 5 z the power of minus 3, right? And similarly on this side, if you take x common, x of z common, what do you get? 1 minus z the power of minus 1. Okay. Now divide both sides by x of z. This also by x of z. And divide both sides by this factor because I need output divided by input. Okay. So what will be output? Y of z divided by input x of z. What do you get? On this side we have 1 minus z the power of minus 1 divided by this factor here. Take this on the other side, it will be the denominator. So 1 plus 3 z the power of minus 1 plus 5 z the power of minus 3. So what is this function? Once you transform your system into z domain, and if you write y of z divided by x of z, output in z domain divided by input in z domain, we call it h of z. The transfer function, the system equation of this system is this one. Similarly here, if you take y of z common on this side, so this common take y of z, then y of z divided by x of z, take this on the denominator here, here. So you'll get what? H of z. So this is the transfer function of this system. When you discuss z domain, there is an equation called transfer function, h of z. What is h of z? By definition, is output divided by input, but in z domain. So y of z divided by x of z, input in z domain, we call it the transfer function of the system. So you can see here, impulse response, when you transform it into z domain, it will give us h of z. H of n is in time domain, the equation, the sequence which represents the system. If you know h of n, you can determine what are the characteristics of h of n. Totally represents your system, but it is in time domain. If you transform it into z domain, it becomes what? H of z. We call it transfer function. Okay. So next time we'll see the how we can determine poles zeros of a system, how determine stability from pole zero plot, and so on. Okay.